Okay, so with our different energy levels in our atom, what the phenomenon is that can happen is if the electrons absorb energy, so energy means they're taking it in, okay? So if electrons absorb energy, so today we're going to use two different forms of energy in our lab. We're going to use fire, so we're going to use heat and put that into the atom, and then we're also going to use electricity and send electricity into an atom. So both forms of energy can cause the same thing, but then sometimes how it looks to us is different. So when the atom absorbs that energy, it takes it in, and then it can jump up to a higher energy level. And the more energy it absorbs, the higher it can jump. Okay? But just like in all things of life, what goes up must come down. So eventually the atom, or the electron, sorry, can only stay in this excited state, that's what we call it, for so long. Just like kind of as humans, you can only be excited for so long. After being excited, it kind of wears you out, right? That's why I go home every day and I'm so tired because I've been excited about chemistry all day long. Okay? So you have all this energy, the electrons are excited, but eventually they have to fall back down. But what happens is as they fall, bam, they release energy.
That actually kind of scared me. I just saw the thing come off for like milliseconds.
So the energy comes flying back out when the electron falls back down. So on your picture right there, that's what this wavy line is as the electron falls, energy comes out, because energy is in the form of a wave, like we talked about last time. Now with this wave, I want you to label it. It comes out in the form of visible light. And that's what we're going to see today in the lab. If you think of our chemistry triangle of all the different sites, so what you're going to see is you're going to see different colors. But what's happening at the molecular level are these electron transitions of it jumping up, falling down, and putting out colored light. Okay? So we call it emitting when it releases the energy. So absorption is taking it in, emission is putting it out. Now, some terminology as we talk about these electron transitions. Electrons are the most stable at the lowest available energy state that we call the ground state. Makes sense, right? They haven't jumped yet, so they're on the ground. What's important to recognize, though, about the ground is n equals 1 is not the only ground state. The ground state is whatever is the lowest for that electron. So if the electron is on the third, then that is its ground state, okay? Because they all can't be on n equals 1, because how many electrons can live on n equals 1?
2.
Only 2 total, right? Okay? Now, anything above the ground state we call an excited state. So anything above the ground is considered excited. Anytime it moves up, that's kind of the word we use. Now, if I'm talking about transition, so for a smiley face, don't say it out loud, but fill in this blank. So if an electron moves from n equals 1 to n equals 3, is energy being absorbed or emitted? Write that in on that line. So fill in this blank for me for a smiley face. So it's going from n1 to n3. Is energy being absorbed or is energy being emitted? Now, even if you think you're wrong, I encourage you to write it down on the paper. Because there's a thing that your brain does when you make a mistake and are willing to make it, that your brain says, hey, don't do that again. But if you aren't ever willing to actually make the mistake, your brain can't ever learn to not do it again, and then the time you're going to do it wrong is on the test. All right, so don't be afraid to make mistakes now because we learn from them. Good. If you said, let's shout it on the count 3. Ready? 1, 2, 3. Absorbed. Have a smiley face. Very good. So how do I know that energy is being absorbed in this transition? Yeah, Haley. Perfect. Right? It takes energy for me to get up on this chair. Right? Just like it takes an atom energy to get to a higher energy level. Good. So then obviously the next answer would be the opposite because now it's going down. So now energy is being emitted. or release. They mean the same thing. And the biggest thing about all of this process is energy is conserved. The same amount of energy it takes an atom to move up is the same amount of energy that is released. That's what's kind of different between maybe us and atoms, right? Because I don't feel like when I move up, it takes me energy. When I go down, I don't release energy, right? But for them, it's the same amount. If it took 10 kilojoules to go up, then they'll release 10 kilojoules when they come back down. So, all done?
It's kind of like a science.
Is there any left of the solution? Yes? Okay. So stick them in the solution and soak them as much as they can. If not, we'll make some more solution real quick. Okay, take a look at these 4 pictures here, okay? And what I'd like you to do with your table buddy is first off, so number 1, I want you to identify the transition that's happening, and I'll do an example for you. And then the second thing is I actually want you to identify of these 4 atoms, so we have our different colors of light coming out. I want you to label each wave as what color it is given these 4 choices. Okay, so the 4 choices are, one of them is violet, one of them is red, one is blue, and one is green. Okay, so for the transition part, so on the line, so I'll do C for you. That's right in front of me. So the transition for C is you look where the arrow starts. The arrow is on, so this is 2, 3, 4. So it's starting on n equals 4, and it's transitioning to n equals 2. So that's what I mean by the electron transition, is where's it starting and where's it going. Okay, so now with your table buddy, figure out the rest of the transitions, and then see if you can determine which atom would be giving off which color. Okay, ready, set, go. You talk with your neighbor about it. I don't want to see it again. So label the transitions. And then see if you can identify which color would be which. And think about, you can go to like our first page of notes when we talked about colors and waves.
So you just get the first number by where it starts, like right here. So n equals 4. I mean, n equals 5. It's in that line. It's super easy, and then you just go where it's going to, which is 2. And then you just do that for all of these, and then we're trying to figure out which.
So the C is
Set your pencil down when you have an answer all 4. Okay. All right, is there someone by raise a hand who would be willing to tell us the answer for atom A? So what color's coming out and what transition is happening? Go for it, Emily. Good, so we're going from N6 to N2, and what color do you think it is? Why would you say it's violet? Good. So we talked about the order of the rainbow, right? Roy G. Biv. That order goes in order of increasing frequency. So yeah, violet waves are going to be a lot tighter than the other waves. Good. The other connection I want you to recognize is notice that this, of all the transitions, is the biggest, right? It's falling from N6 to N2. So the farther the atom falls, the more energy it puts out. And so the more energy it puts out, it shifts the color.
Do we have more of this?
No. We were looking for some. That's what I was going to check, and I forgot.
Okay, I'll go check.
Because no one did the lab on Friday, so I didn't think about it. Yeah, I was hoping that they might, because we have other ones, but they have rubber on them, so they'll melt.
I know, yeah. I was like, yeah, you can't do that.
So, just like
My other thought was you could maybe hold it with test tube clamps, actually.
Okay.
'Cause you just need to be a little bit
farther.
farther. Okay.
I'll go see if I
Okay. Good. Emily, plus my face. Good answer. Okay, second one. B, someone want to tell us what this one is? Yeah, Kate.
I did N4 to N2.
Good. And what color would you predict?
Blue.
Perfect.
that's
It's in
Oh,
Oh, N5,
you're good. Awesome. And once again, you would not have to know the color if there wasn't the comparison. Like, you don't have to memorize that this is exactly how a blue wave looks. It's the matter that we have the comparison of all four. So, good, Kayla. Now smile face for that. Okay, I already gave you transition for C, but someone want to predict the color? Mary?
Green.
Good. Have a smile face for that. And then anyone want the freebie of D? Kiana?
Red.
Good. Red would be the color.
And then it's N3 to N2. And it's the lowest frequency.
Yeah. I think we talked about it last time, right? When we talked about energy. Did we talk about lasers?
Yeah.
Right? You know, so like when red light comes out, it's lower in energy than actually when violet does. So, very good. Yeah.
Letter D, the second one is 2.
Oh, I wrote one. She said 2, but I wrote one. I wrote the answer wrong. Thank you. Okay, questions on this transition? Now, what's going to happen, so there's 2 parts to this lab, like I said. The first part is flame. The second part is electricity. The same thing is still happening in both cases where we're putting energy in, the electrons are going to jump, and then they're going to fall, and then we'll see the color that comes out. Now, the way your eyes work, if you didn't know this, so when light comes at your eyes takes all those colors of light and blends them into the color that they make together. So when we go to the flame part of this lab, you're only going to see one color. But then what's going to happen is when we do the electricity side, is we're going to look at them through these super fancy glasses that separate the wavelengths into different colors. So with our different wavelengths, that we'll see, so they'll end up looking, so in the second half, so you won't see this with the flames you'll just see one color, but in the second half, you'll see some spectrums that look like this. Okay, so these right here, if you can't tell, are different atoms. So this is like krypton, this is baryon, this is xenon. Okay? And the cool thing about these spectrums is they are unique. Every atom has its own spectrum, and no other spectrum is exactly the same. They often compare it to like a fingerprint for the atom. So this is actually one way in which we can identify what an element is. If you do not know what it is, you can use this method to figure it out because it has a unique fingerprint. Yeah?
If you don't know what it is, just chuck it under some flame and see what happens.
Yeah. One of them, I mean, there's various methods to figure out an unknown, but that's one of them literally is just to burn it and then, yeah, see what colors it puts out. Now, with these spectrums, this is actually a way in which scientists have figured out elements in the universe, and particularly with like stars and like the sun. I don't know if you've ever thought about it before, but it's not like scientists flew up to the sun, gathered some sun sample, flew back to Earth, and then analyzed it. Can't really gather sun sample, right? It's a burning ball of gas. But using spectroscopy, they've actually been able to figure out what elements are in the sun and what are in the stars. Okay, so we're going to take a look here. We're going to skip this for now since it's early update. We'll come back to it in a second. Okay, so the way this works, I'll pull this screen down. This bottom spectrum right here is a spectrum for a star. So the star has multiple elements inside of it. Okay? these right here are the spectrums for different elements. Now, what we mean by fingerprint is that where the black lines are unique to that element. So like magnesium always has a very black line in this exact spot, and not very many others. Okay? So now, first off, recognize there's two different ways to take spectrums. It's the same thing, they're just like mirrors of each other. So the ones I showed you on this slide, right here. So notice that these are mostly black with a few colors. But the ones we're looking at now are mostly colored with a few black lines. But if you took that one and this one and put them on top of each other, it'd be a complete rainbow. So it just depends on what equipment you use determines what picture you get. So the one you guys are going to see in the lab today are going to be the ones that are mostly black with the lines. Okay? What they mean is every line corresponds to different electrons falling. Because you got to recognize here, atoms have lots of electrons besides hydrogen. Even hydrogen, its one electron can kind of do multiple falls in the atom. And so every color that you see corresponds to different electrons or different falling transitions. Okay? So I'm going to do the first one with you, and then I'll have you try the second two for a smiley face. So if this is my mystery star, the first thing you look for is you see you're only comparing down. So think of if I took calcium's spectrum and put it on top of the mystery star, does every single black line line up in both? Jacob, which ones do you see that don't?
The ones in the blue.
Yeah, I would agree, right? Like this one has, now once again, we're comparing down, not up. But I even see this one. So this one has a pretty dark line here. But if I carry it down, my mystery star does not. So I would say calcium is not in this mystery star. Because if calcium was, then that line would have to be here. Okay? Hydrogen. Shake your head yes or no. What do you think? Do you think it's in there? Do you think it's not? So hydrogen really only has two distinct lines. And if I look at both of them, I'm just going to grab my ruler, they look like they both appear down below. So I would agree that hydrogen is in there. Iron, shake your head yes or no. What do you think? Yeah, I would definitely say iron, because this one has very dark lines here, and iron is actually the only one that has that. And then magnesium, because it really has this dark line here, and it looks like it lines up there. So let's check it and see if we were right. Oh, we did not. So what do you think we should remove?
The last one. Magnesium, maybe?
So the only one that I thought, because this one is a little tricky, and it's harder, I know you're farther away. But I would actually say, because hydrogen was the one that I wasn't as sure about. Or did I not check one? So let's take away hydrogen. Oh, and it's still saying we're wrong.
I think we would, yeah.
Oh, did I not select one? But it says the mysteries. Oh, it does need hydrogen because we need that line there, right? So then it had to have been the magnesium. There we go. Okay, so number 2, and you can talk with your table buddy about it, is so here's our new mystery star. Did it give me a new one? It's the same. Let's click again. Okay, so here's your star on your little box at the bottom. So this is number 2. Take a guess, and I know it's a little bit of a guess here, but take a guess of what elements do you think are in our mystery star. Ready? You got 30 seconds. Go. Set your pencil down when you've taken your guess. Okay, anyone willing to share their guess out loud of what they think? Okay, Kiana, which ones do you think?
I said calcium and hydrogen because they have the same lines, and then iron and magnesium both have this one dark line in about the same spot that doesn't show up on the mystery star.
Anyone want to disagree? All in support? Correct. If you said what Kiana said, you can have a smiley face. Kiana, you can have 2 for sharing. Okay, let's try one more. So here's your mystery star. Identify the element present. Set your pencil down once you've taken your guess. Once again, the biggest mistake when we look at spectrums, and this actually corresponds to ICANN of 10.4b, is if I give you a spectrum, can you identify what's present, is comparing up and not comparing down. That's where some students kind of get confused. And sorry, I know if you're in the back, it might be a little bit harder to see the lines.
I think it's because the projector's like moving.
Projector's moving?
Like every time somebody takes a step upstairs, it like jiggles a little bit.
Oh. Okay, anyone willing to vocalize their guess? Jacob, what do you think?
Iron and calcium.
So Jacob says iron and calcium. Anyone want to disagree with Jacob? Sage, what do you think?
Magnesium.
So you think magnesium should be included as well? And I agree, that's kind of a hard one because it's hard to tell. I need like if that line matches up with that one or not. That's a hard one. That magnesium line is tricky.
Wouldn't the line on the bottom be darker then?
That's kind of what I'm leaning towards, is since it's not as dark, I think it might not be. But it does line up position-wise. So let's check this. Oh, and we are correct. Okay, so if you said calcium and iron have a smiley face, Jacob, you can have 2. All right, go ahead now and look at your blue paper.